Okay, so this is for our second week's discussion, and this is regarding the topic of sensitivity and specificity. So sensitivity and specificity are normally discussed and predictive positive and predictive negative values. Sensitivity and specificity are often assessed in the laboratory for screening tests prior to them being used in the field. So every drug test, every pregnancy test, every genetic test has a sensitivity and specificity calculation. And then the field application of that sensitivity and specificity calculation is looking at positive predictive value and negative predictive value. Okay, so this week you are going to see what it's like to estimate how many positive cases you're going to find and how many negative cases you are going to find. So the first step in this, and it's very important that you follow these bullet points step by step, is find the prevalence of a disease in the United States. Any disease you want, tuberculosis, HIV, obesity, diabetes, Alzheimer's, stroke, whatever you want, find the prevalence of that disease in the United States. And for any year, it doesn't really matter. Now, this next part is kind of tricky. Find a screening test. Now, for obesity, the screening test would be something like BMI. For diabetes, it could be a blood glucose test, or it could be hemoglobin A1C. For tuberculosis, you could pick something like the TB skin test or the PPD. So you're going to find a screening test for that disease. Once you found the name of your screening test, you want to go to your favorite internet search engine and type in the name of the test as well as the terms sensitivity and specificity. And it will automatically give you the percentages of sensitivity and specificity for that given screening test. Now, this next part of the discussion is where everybody has a real challenge. And that's apply the portion to a random population of people of 100,000 people. So let's look at what that looks like down here. So, disease X. This is a made-up example. My prevalence rate is 10 per 100,000 population. And I have a table down here that gives you a breakdown of how to input the numbers. 10 is everybody with the disease. That's the estimated prevalence. So A plus C, all people with the disease, is 10. Now, 100 is all people without the disease. So we're going to look at what that looks like in a second. Now, based on my made-up screening test, and remember, in your example, you will use whatever sensitivity and specificity your screening test is. You will put the sensitivity, the percentage here. Oh, shoot. I'm sorry, 1 second. You'll put the sensitivity here. I have the sensitivity at 95%. And you will put the specificity here. Okay? Now, the sensitivity and specificity are A plus C equals 100. So 95%, 1 minus 95 gives you 5%. And that's how you know what goes here. B, again, 80 minus 100% is 20%. Okay? So this is the first step that you have to put in your discussion post so that you can understand how to work the math appropriately. Now, if you look at step 2, I input all the numbers. The 10 goes here because that's everybody that's sick, and the 999,990 goes here because that's everybody that's well. Because remember, the total population is 100,000. The total well population is 100,000 minus 10. Okay, so this is the sick, this is everybody, and this number represents everybody minus the sick. And then again, multiplying 80% by that 999,990 gets you the 799,992. And multiplying the 20% by the 999,990 gets you 199,998. So this gets you the populated version of your table. Now you have to calculate the predictive positive and the predictive negative value. Now, the predictive positive value is A over A plus B. And that equals the positive predictive value. Whereas the negative predictive value is D over B, C plus D. And this is the negative predictive value. Okay. So you input these numbers in this formula to generate your positive predictive and your negative predictive value. Now, why is this important? Because as incidence increases, positive predictive value increases. So that means of your screening test. So that means the more people within a population that have the disease and you decide to screen everybody for that disease, the higher the probability you're going to find somebody. And as incidence decreases, or the disease is rare, negative predictive value increases, or the strength of your negative result. Okay? So let me give you an example. We want screening tests to be cheap. The reason we want screening tests to be cheap is because we're using them on 10,000 people. We can't use, in a TB example, we cannot use quantiferon gold to screen 10,000 people for TB because the quantiferon gold test costs $600 and the TB skin test costs $25. Even though quantiferon gold is a better test, it does not meet the economic return on investment. So this is how you populate the math. So we are talking about applying a proportion to the random 100,000, calculating the predictive positive value and the predictive negative value. Now you have to answer the question, does it make sense to screen for this disease using this test based on the natural history of the disease? Now, this is something that you have to research and find out. Is universal screening recommended, or is screening recommended based on a given population's risk? All right, and so this is the rest of the prompt. From this point, you can easily calculate the predictive positive and the predictive negative values. The real challenge is going to look at the natural history of the disease and cost of the test to determine if screening is appropriate. And so you will have to make sure that you have all research cited. You'll have to show all of your work in step 1 and step 2. So what I'm going to do now is stop the screencast recording and make this available on YouTube so you can re-watch this, and then we'll start answering questions.